Last class, we spoke about edge detection and went into details of the canny edge detector. And this lecture, we'll move a little forward and talk about other kinds of artifacts from images that are practically useful, specifically blobs and corners. Before we go there, we did leave one question for you at the end of the last lecture. Hope you spend some time working out the solution yourself. If not, we'll briefly discuss the outline right now and wait for you to work out the details yourself. So we talked about trying to use canny edges to get straight lines in images. How do you do this? You first compute canny edges in your image, which means you would compute your gradients in the x direction and the y direction, and you could also compute your thetas, which are your angles of each of your edges, which is given by tan inverse of gradient with respect to y divided by gradient with respect to x. Now, as the next step, what we do is assign each edge to one of 8 directions. 8 is just a number. You could choose anything else, but you assign each edge to one of 8 directions. So you probably combine several edges into a single bin. And for each of these 8 directions, let's call one of those directions to be D, we obtain what are known as edgelets. And what are edgelets? Edgelets are connected components for edge pixels with directions in D-1, D, and D+1. So for a given, so you have 8 possible directions that you bin all your edge orientations into, and you take one of them and connect them with edges with orientation D-1 and D+1. So you get a set of what are known as edgelets. Once you compute your edgeless, we then compute two quantities, straightness and orientation of the edgelets. And the way we go about doing this is using the eigenvectors and eigenvalues of the second moment matrix of the edge pixels. So what we do here is you have your edge pixels that belong to a particular edgelet. So you take all of those pixels and compute such a matrix. Remember, the matrix is given by, so if you look at the first entry here, the first entry here corresponds to x minus mu x. Mu x is the mean x dimension of all of those pixels in the edgelet, and each x corresponds to one of those x coordinates of one of those edgelet pixels. So you're simply computing, in some sense, a sense of variance with respect to the mean edge pixel along the x direction. Similarly, you have a variance of the along the y direction of those edge pixels with respect to their means, and you also find the covariance with respect to x and y directions. So once you have this, very similar to how principal component analysis happens, we take the eigenvectors and eigenvalues of this second moment matrix, and remember, the eigenvector and the eigenvector corresponding to the largest eigenvalue will give you the direction of the maximum variance among these pixels, and that's what we are looking for at this time. So we finally decide that the orientation of the edgelet is going to be given by tan inverse of V1 by V0, where V1 is the larger eigenvector. By larger, we mean the eigenvector corresponding to the larger eigenvalue. Remember here that M is a 2 cross 2 matrix, which means you'll only have 2 eigenvalues at maximum, and you're going to take the eigenvector corresponding to those to the larger eigenvalue, and we call that to be V1, and V0 is the other eigenvector. So if you take a tan inverse of these two vectors, that theta will give you the direction of that overall edgelet. Okay, so in case you are finding this difficult to understand, please go back and read principal component analysis, and you'll be able to connect that to this particular idea. And we define straightness to be lambda 2 by lambda 1, where lambda 2 is the second largest eigenvalue and lambda 1 is the largest eigenvalue. So the straightness here is going to be the highest value when both the lambda 2s and lambda 1s are equal, close to equal. And once you get this quantity, you just threshold the straightness appropriately and store your line segments. So it really doesn't matter whether you measure straightness as lambda 2 by lambda 1 or lambda 1 by lambda 2. You just have to ensure that you construct your threshold appropriately. If you invert the straightness ratio, you just have to ensure that you threshold it at a appropriate value and then obtain your line segments. So here is a visual example. So you can see that after applying Canny, you get all these edges on the left. So you do get lots of edges which are fairly well connected, not too noisy, but not all of them correspond to straight lines. Many of them correspond to edges that represent, say, the texture of the floor and so on and so forth. But we really don't want that when we model, let's say there is an application where we really don't want it. So then you use this kind of an approach to obtain just the straight lines from your Canny edges. Okay, think more about this, you can, I think knowing more about PCA could help you understand this a bit better. Moving forward, as we said, the focus is going to be going from edges to newer artifacts such as blobs and corners. So remember last lecture, we talked about taking the Laplacian of Gaussian, and we said that taking the zero crossings of the Laplacian of Gaussians could give you a measure of edges in an image. That was another way you could obtain edges in an image. We're going to talk about it slightly differently now. So once again, just to recap, remember, this is your Gaussian, this is your derivative of the Gaussian, and this is your Laplacian of your Gaussian, where the Laplacian we defined as grad square f is equal to dou square f by dou x square by plus dou square y by dou y square. Now, let's say an example of a 3x3 Laplacian of Gaussian filter is going to look somewhat like this, where you have a -4 in the center and 1, 1, 1, 1 in its nearest neighbors and 0, 0, 0, 0 in its next level of nearest neighbors. But can you try to guess why this is a relevant Laplacian of Gaussian filter? Okay. One point to notice here is an equivalent Laplacian of Gaussian filter could also have been 0, 0, 0, 0, -1, -1, -1, -1, and 4. So if you actually visualize this filter, you would see that at the center there is a peak. At its immediate nearest neighbors, there is a -1. There is a value that goes below, underneath your 0. And then there are zeros in other places. So if you try to visualize, this filter would be very, very similar to the shape of the Laplacian Gaussian that we just saw on the earlier slide. Okay? But that's from a geometric or a conceptual perspective. Why did we say 4? Why not 8? Why not any other number? Once again, it goes back to approximating the gradients in some manner, and we can work this out to show you how this works out. So remember, we are computing second derivatives here. So dou square f by dou x square can be written as, in approximating using first principles, you can say it's f of x plus 1y plus f of x minus 1y minus 2 f of xy. Similarly, you can write it out for dou square f by dou y square. Now, if you try to put both of these into your Laplacian of Gaussian equation, or your Laplacian equation in this particular case, you would then have grad square f is equal to f of x plus 1y plus f of x minus 1y plus f of x y plus 1 plus f of x y minus 1 minus 4 times xy. This should straight away ring a bell for you as to why you got this kind of a filter. Remember, at f of xy, the coefficient is -4. At its neighbors, x plus 1, x minus 1, and similarly y plus 1, y minus 1, the coefficient is 1. So this simply came from taking an approximation of the gradient. Remember, you could have other kinds of approximations of the gradient with respect to the local neighborhood. You could consider a larger window, so on and so forth. If you do that, obviously the definition of the Laplacian of Gaussian filter would have to be appropriately modified. Here is another visual illustration. Here is the original image. Here is simply taking the Laplacian, and here is the result if you take the Laplacian of Gaussian. Remember again that Laplacian of Gaussian gives you the smoothing effect, which smoothens out the noise and then takes the Laplacian of your original image. Once again, remember that we are just taking a filter and convolving the filter by moving it around at every point in the image and getting your output. Now let's ask the question. So this is something that we partially saw the last time, right? So what else can Laplacian of Gaussian do? Do you have ideas? The other thing Laplacian of Gaussian can do is detect blobs. Why? Remember that a Laplacian of Gaussian filter looks somewhat like this. Remember, you could write the Laplacian this way or the other way. It really doesn't matter, right? So at the end of the day, for edge detection and similar detection of other artifacts, we only take the absolute value. Whether the output is negative or positive, we just take the absolute value. So that would change if you had a white circle with a black hole or a black circle with a white hole. We ideally do not care. Both of them are blobs to us, and we ideally want to recognize blobs in both these cases. So you could write your Laplacian of Gaussian this way, or another way where your central peak goes up on top, so and the other part comes below. This is similar to writing the Laplacian of Gaussian with a -4 in the center and 1, 1, 1 around, or a 4 in the center and -1, -1, -1 around. So now if you try to visualize this as an image, so if you took a Laplacian of Gaussian filter, a 3 by 3 may be too small. Let's say you expand it, take a larger neighborhood. Let's say you take a 7 by 7 Laplacian of Gaussian filter or 11 by 11 Laplacian of Gaussian filter. You would find that the Laplacian of Gaussian filter, just the filter itself, remember that's also a matrix that also can be visualized as an image, would look something like this. A black blob in the middle, a white ring, which is where you have a peak, and gray all the way in other places. You could also have an invert of this, where you have white in the middle, a black ring, and then gray all over. Right? Both of these are similar. And by looking at the filter, you can say that it's likely to detect blobs. In some sense, convolution of the filter can be viewed as comparing a little picture of what you want to find against all local regions in the image. Okay. So there is a slight nuance which is different. This does look a bit similar to template matching, for which you use cross correlation, but in convolution you would double flip the filter and search for that across the image. But when your filter is symmetric, it really does not matter. Both cross correlation and convolution will be looking for the same filter in the image. So once you have a Laplacian of Gaussian like this, you can probably count sunflowers in a field, or you can probably detect red blood cells in your blood tests, any structure with blobs across an image. Clearly, in this image with sunflowers, there are blobs of different sizes. So you would have to run a Laplacian of Gaussian with different blob sizes to be able to capture all of those blobs in the image. Let's now move forward to the next artifact, which is very useful to extract from images. For a large part, extracting corners from an image was a very, very important area of research in computer vision in the late 90s and early 2000s, probably entire 90s into early 2000s. So we'll try to describe one popular method today, and let's start by asking the question, suppose we had an image such as this. What would be interesting features that set apart this image from any other image? Remember that if we want to do any processing, we want to be able to extract some unique elements of the image. So what are those unique elements in this image? And we're going to say that those are going to be your corners. Okay, but let's try to go there. We ideally want to look for image regions that are unusual. Something that sets apart that image, that region in the image from other images. If you have a region that is textureless, for example, the blue sky, then that could be common across several images and it may not really be unique to that particular image. You may not be able to localize that region in any other image with a similar content. You ideally are looking for patches with large contrast changes, large gradients, right? Edges are a good example, but we'll talk about why edges may not be the right artifact in a moment. But we are ideally looking for some patches or some regions in the image which have large contrast changes, such as gradients. But the problem with edges is edges suffer from what is known as the aperture problem. By aperture problem, we'll just see a visual illustration on the next slide. But there, while edges are good, unique aspects of a particular image, they do suffer from a problem, which we'll talk about the next slide. So what we ideally are looking for are regions of the image, or what we're going to call corners, where gradients in at least two different directions are significant. So remember, an edge is an artifact where you have a significant gradient in one direction, right, which is going to be normal to that edge. It could be whatever direction the edge may be. The normal direction to that edge is going to be the orientation of that edge. But we're saying we want those points where there could be significant gradient in two directions. What does that mean? We'll try to answer. Let's take a tangible example. Let's assume that there's an artifact such as this. This looks like some inverted V, let's say. And we have such an artifact and we want to find out which part of this image. Let's assume this is the full image. Ignore the blue box. The blue box is for explaining it to you. Just consider the image with just this inverted V. Okay. We want to find out now which aspect of the image is unique to it, which can help us recognize it, say, other times, or if we view the image from other angles. So if you consider this blue box placed here, you see that that's a flat textureless region. There's no change in intensity in that region. So it's not going to be very useful. It's like the blue sky with absolutely no change. It's not going to be very useful when you try to compare this image with other images. So if you now place the blue box on the edge part of the image, this is good. There is some artifact that's useful, but the problem is if you move this patch here or here, it would all have the same response. Right? You would never know whether you placed your box here or here or here, because all of them would have exactly the same response. There's no difference in the local characteristics in all of these places. So which means while edges are useful, there is something that they're lacking. So which means if you try to match, or let's say you take a panoramic photo in your phone and you try to align two images, you may not know which part of the edge to align at. We are ideally looking for placing the box at that kind of a point where there is change in two directions. And that point could be unique to this particular image, and ideally we're looking for many such points in an image, but such points are the kind of points that we want to detect in an image. How do we find such points in an image? Right? We know how to do edges now, but let's try to go one level further to try to see how do you find such corners in an image. To do that, we're going to define a quantity called autocorrelation. Okay, as the name states, it's autocorrelation. It's correlation with itself. So you're not going to use any external filter. You're going to take a patch in image and see how it correlates with itself. What does that mean? Let's try to quantify that. So we're going to define the autocorrelation function as you take a patch in the image and you compute the sum of squared differences between pixel intensities with small variations in the image patch position. So if you had a point Pi in the image, let's say you place it at the center, that's what is going to be Pi. And if you now have a small delta U, which is going to be the difference, you're going to move that patch by a certain delta u. Remember, pi and delta u are both 2D coordinates, so even delta u will probably have a delta u and a delta v, for instance, right? There are going to be 2 dimensions there. It's a vector, which is going to be, so you take I of pi, which is the image intensity at that point pi, then you move that point pi plus delta u, you move it a little bit, and you see what is the image intensity at that new location, and you take the sum of square differences for all points in that particular patch. So if you take a square patch, take every point, move it a bit, so move that entire box a bit, and then you compute pairwise distances between the same locations in the original patch and the new patch and sum them all up. This is what we define as autocorrelation. About this function W of pi is a function that tells you how much you want to give weight for each particular point in that patch. Maybe for the central pixel, you want to give more weight. For a pixel at the periphery of that square, of that blue square that you have, you may want to weight it a little lesser. So you could have a fixed weight for all points in that square, or you could have a Gaussian which defines W of pi, where you weight the central pixel more and the pixels at the periphery a little lesser. We define this as autocorrelation. Now let's try to see how do you compute autocorrelation, and then come back to how do you compute corners using this autocorrelation. So let's look at this more deeply. Let's consider a Taylor series expansion of your I of pi plus delta u. Remember, pi plus delta u is about taking the patch which was centered at pi and moving it by a delta u and placing it at a slightly offset location in the same image. From Taylor series expansion, you can write this as I of pi plus grad of I at pi delta u, where grad of I at pi is the image gradient at that particular location. Dou I at pi by dou x, comma, dou I at pi by dou y. We know how to compute the gradient, right? We've already seen that so far. Now let's write out autocorrelation. Remember, the definition of autocorrelation that we wrote on the previous slide is this one, where we said autocorrelation is W of pi into I of pi plus delta u minus I of pi squared. Now we're going to replace I of pi plus delta u with this Taylor series expansion. So plugging that in here, you're going to have W of pi, this first term here gets written as I of pi plus delta I of pi delta u, okay, minus I of pi. So just to explain the notations here, by delta of u we mean a vector delta of u and say delta of v. Because this we have taken out a summation here, we are simply writing it as one of those delta of u's inside, right? So anyway, there's going to be a summation for delta v, which will take care of the other component of delta u. Once you have this, you can see that I of pi and I of pi gets cancelled, and you're left with summation over xy W of pi into dou I of pi dou u whole square. And we're going to write that as a quantity delta u transpose a matrix A into delta u. Okay, so remember that you have this delta u square, you just split it into two parts, where you have one part that comes here and one part that goes here, and the rest of what you have, W of pi into dou I at pi, you combine that into a matrix called A. How would A look? A would look like something like this. Remember, A is going to be a combination of W into your dou i's, so which means A is going to look something like this. W of u comma v, you're going to have, remember, two components of the summation, ix square, ix iy, ix iy, iy square. Those are going to be your gradients, and that is going to be your A matrix. So we took the definition, so we defined autocorrelation in a particular manner, where we said we take a patch, move it a bit and see how the image properties change in that local region. So we then took the definition of autocorrelation, played with it a little bit, and then came up with an expansion which looks somewhat like this, and we are now focusing on this matrix A. So this matrix A, so delta U is simply the change that you imposed in the patch location, right? That's what you imposed. A is what is giving you how the gradients changed between those two patches, and a W weighting factor that tells you how much you should weight the central part of that patch versus the peripheral parts. So since A is what defines the intensity change, we're going to consider an eigen decomposition of A, which is given by U lambda U transpose, where lambda is going to be a diagonal matrix with lambda 1 and lambda 2 to two eigenvalues. Remember, A is a two-dimensional matrix, which means the maximum number of eigenvalues you can have is 2, where A of A into Ui is equal to lambda Ui, your standard eigen decomposition, okay, which is wonderful. So we once again started with autocorrelation, wrote it in a slightly more slightly different manner, and then now we have done an eigen decomposition of A. Where do we go from here? How do we go from here to finding a corner? Okay, that's the question we are asking. Think about it for a moment. How do you think you can go from the eigenvalues of A to a position of a corner? Very similar to the discussion that we had at the early part of the lecture. When both lambda 1 and lambda 2 are large, you know that the intensity changes in both directions at those points. When either lambda 2 is much greater than lambda 1, or lambda 1 is much greater than lambda 2, it's going to be an edge, because there's going to be change only along one direction. And if both lambda 1 and lambda 2 are small, you're going to say it's a flat or a textureless region. So which means we know that from the eigen decomposition of A, all what we are looking for is both the eigenvalues to be high, and we know we've probably hit a corner. So let's see how do you actually do this inference. So this another way of looking at it is, so wherever there is a vertical edge or a horizontal edge, you're going to have either lambda 1 greater than lambda 2 or lambda 2 greater than lambda 1. At a corner, you're going to have both lambda 1 and lambda 2 to be large, and in a flat region, you're going to have both lambda 1 and lambda 2 to be very small. So what do we do with this? So the way we are going to compute your corner, this was a method given by a person called Harris, and that's why it's known as the Harris corner detector. It's a very popular detector that was used for several years. Of course, there have been lots of improvements and better methods that people have developed, but this was one of the earliest corner detectors that was developed and was used for many years. So the entire procedure follows something like this. You compute gradients at each point in the image. Using that, you compute your A matrix. You can use a weighting function, or if you don't use a weighting function, you just assume that you're going to consider all of them to be equal, all of the patch positions of that patch to be equal. Then we ideally want to compute your eigenvalues and decide your cornerness based on the eigenvalue. But because eigen decomposition by itself can be a costly process, we try to do a slight deviation to be able to compute our cornerness measure. So we're going to define a cornerness measure as lambda 1 into lambda 2 minus kappa times lambda 1 plus lambda 2 squared. I'll let you work this out to show that when this entire quantity is high, you will know that both those lambda 1s and lambda 2s are high. Work this out for yourself. Try out different lambda 1s and lambda 2s and you'll see what I'm saying. But what is interesting here is lambda 1 and lambda 2 is nothing but the determinant of A, and lambda 1 plus lambda 2 is nothing but the trace of A. Which means we can define our cornerness measure as determinant of A minus some constant kappa times trace square of A. Kappa is just a constant that you have to define to get what you want to get. For different images, you may have to set kappa differently. Why is this useful? you no more need to compute the eigen decomposition of A matrix. You only need to compute your determinant and trace, which is a bit easier than computing your eigen decomposition. Finally, you then take all points in the image whose cornerness measure is greater than the threshold. So you can take lots of different points, probably all points, compute their cornerness using autocorrelation, and then whichever is greater than a particular threshold, you actually call them corners. You can finally also perform non-maximum suppression, where if you find that there are many corners in a very small local neighborhood, you pick the one with the highest cornerness measure. That's your non-maximum suppression that we also talked about in the Canny edge detector. So this non-maximum suppression will keep coming back to us at various stages in this course, at various in various use cases. So here is a visual illustration of the Harris corner detector. So let's consider two images of the same object taken from different angles. The objects are at different poses and the illumination is also different. Let's try to run the Harris corner detector. Ideally, what we want is that in both these images, the same parts or the same corners in the doll get picked. Why is that relevant? Once again, if I take the example of, say, stitching different images in your cell phone, a panoramic mode or something like that, we want the same points in both those objects to be located so that they can be matched and probably stitched together to get a panoramic image, just as an example of an application. Let's see it now. So here is the step of computing the cornerness, where you do autocorrelation, get your cornerness values, and then you take all the high responses by using a threshold. You do non-maximum suppression. That's why you see many of those points in regions. You just take the highest cornerness value, you do the non-max suppression, and now you get a bunch of different points. And now let's try to visualize them on the image, and you can actually see that if you look at, say, these highlighted examples, you can see that although those are fairly differently tilted, you can get similar corners in both of these regions. So you can see many other regions too. Obviously, you get a few more corners which are not there in the second image, but those can be overcome at the matching phase, as you'll see a bit later in this course. Okay. The focus of this particular lecture is on cornerness, just detecting the cornerness. How do you do the matching between the two images? We'll come back to that a bit later. While we saw one variant of the Harris corner detector here, which was developed by Harris and Stephens in '88, where we used the determinant minus kappa or alpha times your trace. That's what we used. Here. There have been other improvisations of the same method, where a researcher, Bill Triggs, suggested that you can use lambda naught minus alpha lambda 1, where lambda naught is the first eigenvalue or the larger eigenvalue and lambda 1 is the second eigenvalue. A researcher, Brown and a team, proposed determinant of A by trace of A instead of doing the determinant of A minus lambda alpha into trace square of A. We said kappa on 2 slides ago. That just doesn't matter, it's just a constant. So you have determinant of A by trace of A. All of these could be different ways of playing around with the same quantities to get what you want. All of them effectively try to measure the cornerness using the eigenvalues of your A matrix, which comes from autocorrelation. Let's ask a few questions about properties of the Harris corner detector before concluding this lecture. The first question we're going to ask is the Harris corner detector scale invariant? What do we mean by scale? Remember, scale is complementary to resolution. So if you have an object which is very small in an image, we call that smaller scale, or if it's large, we call that larger scale. So you could have an artifact such as this curved line here in a particular image, or you could also have this curved line on a larger canvas. Maybe you just took one image from close up and another image farther out. but it's the same image, it's the same object that's being taken. So in this particular case, if you observe, in the second image, this point would be considered a corner by the Harris corner detector. But in the first image, if you took the same size patch to do the autocorrelation, you would find that all of these would get categorized as edges and none of them would get categorized as corners, which means the Harris corner detector need not necessarily be scale invariant. How do you make it scale invariant? We'll talk about that later. What about rotation invariant? Is the Harris corner detector rotation invariant? It happens that it would be rotational invariant. So whether you have this particular inverted V like this, or whether you rotate it and have the inverted V like this in an image, this particular corner will have high change in both directions in both cases, and you would detect this corner both in this image as well as this image. As long as there's no change in scale, you would detect the same corner on both images, and Harris corner detector in this particular case would be rotation invariant. What about other kinds of invariances? What about photometric change? What does a photometric change mean? A photometric change is an affine intensity change. Okay? An affine intensity change means that you take your intensity at every pixel in the image, scale the intensity by value A, and maybe translate it by a value B. Okay? Imagine that remember that intensity is a value lying between 0 and 255, or if you normalize it, comes to between 0 and 1. You just multiply all of those values by a scalar, say A, it could be less than 1 if you like, and also add a quantity B if you like. We call that as a photometric change or an affine intensity change. So in this particular case, if you notice, for only the translation, it really does not matter. You would find the corner whether you increase the intensity in all places by an amount or otherwise, it would still find the corner. But about the scaling part of the intensity change, by multiplying it by an A, it depends on the threshold that you choose. Okay. If you had a particular curve, any function for that matter, and you had a certain threshold, all these points which have a certain value, remember that the points closer to that would get suppressed due to non-max suppression. So you'll only have the peak in all of these points. So those peaks would get detected. But if you now scale the curve, there could be newer points that get added. Right? If you scale it up in a different way, there could be newer points that get added. So which means it's perhaps invariant to translation, but not necessarily invariant to scaling the intensity. A couple of slides back, we spoke about invariant to scale with respect to size of the artifact itself. Now we are talking about scaling with respect to the intensity value. Hope you see that these are two different things. In this case, you could still have a curve which is small, but now you brighten it or darken it in a different way. And that's what we mean as an photometric change in this particular context. So the homework you're going to have is to go ahead and continue to read your chapter 2 of the Selinsky's book. And since a lot of the concepts that we used in this lecture were based on eigenvalues, eigenvectors, just go ahead and brush up your linear algebra. Try to show that the trace of a matrix is the sum of its eigenvalues and the determinant of a matrix is a product of its eigenvalues.